This video is going to take you through part 1 of chapter 2, section 3, in which it's titled Polynomial and Rational Functions, but we're going to talk about a lot of different topics from Algebra 2, including long division, synthetic division, finding possible roots, finding actual roots, and then we're going to get into how to use the calculator to help us with some of that stuff. So we start with long division, and it is exactly what it sounds like. It is long and tedious, but it is the same steps on repeat. So if you practice them, it's not terrible. This is like the written rules, and what it says first is arrange the terms of both the dividend and the divisor in descending powers of the variable. So dividend and divisor, what you're dividing into is the dividend, and what you're dividing by is the divisor. If it's in fraction form, it would be dividend over divisor. And so what we're going to do is take our expression. So let's say I've got x to the third plus 2x minus 3x squared plus 1. And I want to divide it by x plus 2. So the first thing I'm going to do is rearrange them in descending powers. If you look at this first example, or the first one, it is not in descending powers. It starts with x to the third, but then it jumps to x to the first. So we would have to rewrite that as x to the third minus 3x squared plus 2x minus or plus 1. I had to do the same thing with what you're dividing by or the divisor. This time there's only 2 terms, but if there were 3, I would make sure that it was in descending degree power. And if there's something missing, so for example, if I had said instead I'm dividing this by x squared plus 2, I'm going to plug in placeholders. So that would look like x squared plus 0x plus 2. You have to do the placeholders in both the dividend and the divisor so that the terms will line up when you go to multiply these out. All right, then step 2, divide the first term in the dividend by the first term in the divisor. So we're basically saying, what do I have to multiply this first term to get to this first term? Just first into first, and it x to the first power. Then we're going to multiply every term in the divisor by the first term in the quotient. So we're going to take this and we're going to multiply it times each term. So x times x squared is x to the third. X times 0x would be positive 0x squared. And x times positive 2, positive 2x. And then this says subtract the product from the dividend, which is an option, but less mistakes are made when you change your signs and add. So we're going to do that instead. Instead of subtracting, we're going to change these signs, and then we're going to add our terms. We're adding vertically. And when you add, if you've done it correctly, the first term should always cancel out. Then I would carry this negative 3x squared plus, I'm going to keep that placeholder, and then I'm going to bring down the next term, which is that plus 1. And then I repeat that whole process all over again. I divide first into first. What would I have to multiply x squared by to get to negative 3x squared? It's negative 3. And I multiply times each term on the outside. So I'm going to multiply negative 3 times x squared, and I get negative 3x squared. Multiply negative 3 times 0x, negative or positive 0x, and multiply negative 3 times positive 2, and I get negative 6. And then we're going to change our signs, and the first terms cancel as they should. The second term also cancels this time. It doesn't always happen, but it does this time. And our remainder is 7. So then it says use this new expression as the dividend, repeat the process. So we did that. And then we're going to express our answer as the quotient, which is what's at the top, plus the remainder, which is what's at the bottom, over the dividend, which is what we divided by, x squared plus 2. All right, we're going to practice that a couple of times. So in example 1, it says divide 9x squared plus 6x plus 5 by 3x minus 2. I want to make sure it's in decreasing degree order, and there's no term missing. There's neither of those happening this time. So I'm going to rewrite 9x squared plus 6x plus 5 divided by 3x minus 2. And it is first into first. So what would I have to multiply 9x by to get to 9x squared? It's 3x. Multiply it, and I get 9x squared. Multiply it by negative 2, and I get negative 6x. And then we change our signs. First terms cancel. 12x remains, and I bring down the positive 5. And I repeat that process again, first into first. So what do I multiply 3x by to get to 12x? It's positive 4. Multiply it times the 3x, I get 12x. Multiply it times the negative 2, I get negative 8. Change your signs. This cancels. My remainder is 13. And I rewrite my answer as quotient plus remainder over divisor. All right, example 2, again, long division. I'm going to check my first, what I'm dividing into, and this time I'm missing an x squared, so I'm going to add a 0x squared. Check what I'm dividing by, and they're all there in decreasing degree. So x to the third plus 0x squared plus 3x minus 2 divided by x squared plus 5x minus 3. First into first, so I'd multiply by x. I'm going to multiply all three. X to the third plus 5x squared minus 3x. Change your signs. Cancels. Negative 5x squared plus 6x. Bring down the minus 2. First into first again. Multiply by negative 5 this time. Negative 5 times x squared. Negative 5x squared. Negative 5 times positive 5x. Negative 25x. And negative 5 times negative 3, positive 15. And we change our signs. Cancels. 31x minus 17 is the remainder. So I'd rewrite it as quotient plus remainder over divisor. The division algorithm is a fancy name for saying if the remainder is 0, then we say the divisor divides evenly into the dividend and the divisor and the quotient are factors. Basically, if our remainder is 0, then what we divided by is a factor of what we divided it into. So if we want to know if something is a factor, then we would divide it by the divisor. And if the remainder is 0, then we would say it is a factor. All right. Next up is synthetic division. Now, synthetic is definitely easier, and you'll hopefully remember it when we start to go through the motions. But synthetic cannot be done every time. Long division can be done every time, but synthetic can only be done if we are dividing by x plus or minus a single number. So our x cannot be squared. It can have a coefficient, but then you're dealing with a fraction on the outside, and we don't want to do that. So we typically would not even do it if it said something like 3x plus 2. We would only do it if we're dividing by x plus or minus a number. So now let's say I had x squared plus 3x minus 5, and I'm dividing by x minus 2. So I know I'm going to do synthetic because it's x minus 2. And the first step is to take what follows. Well, first I'm going to take both of my divisor and my dividend and check the same thing we did for long division. Is it in decreasing degree order? Have I skipped any terms? If not, then I'm going to arrange, which is step 1, okay? Then, given x minus c is what I'm dividing by, I'm going to write c to the left, which means I'm going to change the sign on what follows. And I'm going to put just a positive 2 to the left. And then I'm going to list all the coefficients of my trinomial here, or my dividend, which would be 1, 3, negative 5. So I ignore all the variables. Then I bring down the first term. So I bring down the 1. I multiply what's on the outside by that number and put it in the next column. So 2 times 1 is 2. Then I add. So I'm going to add those two together. I get 5. And then I repeat. Multiply by what's on the outside. I get 10. Add, and I get 5. So I repeat until all the columns are filled in. And then the last term is your remainder. So 5 is my remainder. And the degree of the first term is 1 less than the degree of the dividend. What I divided into was x squared. So this one's going to get x to the first. And the 5 is the constant. The other way to look at it is the last term is my remainder, and then the next term gets no variable, the next term gets the x. So my quotient is x plus 5 with a remainder of 5, so plus 5 over my divisor, which is x minus 2. The great thing about synthetic is it's fast. It eliminates a lot of the writing of your variables out. It's easy to make a mistake here because we go a little bit faster, so be very careful when you're doing these. Here we go. Example 3, divide 5x to the third plus 6x plus 8 by x plus 2. That is x to the first, followed by a number, so I can do synthetic. I'm going to look at my dividend. I'm missing an x squared, so I'm going to plug in a 0x squared here. Change the sign on what follows the x. So negative 2 goes on the outside, and then I list 5, 0, 6, 8. Bring down the 5. Multiply by what's on the outside, negative 10, and add it. Multiply by what's on the outside, 20, and add it. Multiply by what's on the outside, and add it. This is my remainder. The next term is my constant. The next term gets x to the first, and the next term gets x to the second. So my quotient is 5x squared minus 10x plus 26 plus 60 over x plus 2. All right, here we go again. This time it's just written stacked, but it's the same thing. Divide using synthetic division. Looking at what I'm dividing by, a positive 4 goes in the outside. I'm not missing any terms this time, so I'm going to list all the coefficients and the constant. Bring down the 3, multiply by 4, put it in the next column, add it. Multiply by 4, put it in the next column, add it. Multiply it by 4, put it in the next column, and add it. The last number is your remainder, then the constant, then x to the first, then x to the second. So we get 3x squared plus 7x plus 35 plus 132 over x minus 4. All right, now we're going to talk about the remainder theorem. The remainder theorem says if a polynomial f of x is divided by x minus c, then the remainder is f of c. So what we can do is take something that we would normally have an f of x, and if it had asked you to find f of 2, up until now we would have taken 2 and we would have plugged it into all the x values. Well, what the remainder theorem says is if we actually take that 2 and we put it to the outside, and we list all the coefficients and the constant, and we divide synthetically, the remainder of this is the same thing I would get by doing f of 2. So in some ways, it will be shorter to just plug it in. If it was like linear or something like that, it's going to be shorter to plug it in. But if it's something that has a higher power, or you're multiplying by a bunch of numbers, then it's going to be quicker to do synthetic division. Now notice we don't change the sign when it's inside the parentheses because it's not x plus 2, it is f of 2. So we don't change the sign when it is inside the parentheses, we just put it on the outside. All right, so example 5, use synthetic division and the remainder theorem to find the indicated function value. So we're going to find f of 2 by putting 2 on the outside. We've got x to the third, x to the second. This time we're missing an x to the first. So I write 3, negative 5, 0, and 1. Bring down the 3, multiply by 2, put it in the next column. That's 6, add it, it's 1. Multiply by 2, put it in the next column, add it, it's 2. Multiply by 2, put it in the next column, add it. So f of 2 would be 5. Okay, so now this brings back in that factor theorem, which basically says if f of c equals 0, then x minus c is a factor of f of x. And if x minus c is a factor of f of x, then f of c equals 0. So if you are given a solution, if it says, here's your polynomial, f of x equals blah, 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 and then it says you have a solution that is 3, then we're going to use that solution. So let's say this is an x to the third. We're going to use this solution on the outside of our synthetic division. We're going to go through synthetic division, and we expect to get a 0 at the end because it's telling you it's a factor. So the remainder should be 0. And then the result from this is going to be an x squared, and we'll take that and we'll either factor it, or we can use the quadratic if it's not factorable to find the remaining roots. So you're going to get given one solution. We're going to use synthetic division to bring it down a degree, and then we'll be able to find the remaining 2. If we were given 2 solutions, we would put one on the outside, then we would take our remaining quadratic, put it in the inside, and put the second number, let's say it was said also 4 was a 0. Then we would bring down, and then the remainder would be 0 again, but now we'd only have one term at the end. And that's how we would get our 3 answers. All right, so this question says, solve the equation x to the third minus 7x plus 6 equals 0, given that 2 is a 0. So we're going to put 2 on the outside. We're missing an x squared, so we're going to put the 0x squared there. 1, 0, negative 7, 6. Bring down the first term, multiply, put it in the next column, and add it. Multiply it, put it in the next column, and add it. Multiply it, put it in the next column, and add it. If you don't get a 0 here when it said that it's a 0, then we know we did something wrong, so we're going to check our work. So now the 3 stays 3, the 2 gets the x, the 1 gets the x squared. So I get x squared plus 2x minus 3. And then I'm going to try to factor. If there are factors of negative 3 that sum to positive 2, positive 3, negative 1, now I've found my other 2 factors. I'm going to set this equal to 0 and get negative 3 and positive 1 as the solutions. Since it says solve, I want to include all the zeros, which is the original 0 they gave you and the other 2 I found. Now, knowing what we learned in 2.3, we could actually check this, or in 2.2, sorry, by doing x minus 2, x plus 3, and x minus 1, and checking that it gives us our original question. All right, example 7. Verify the given factors, find the remaining factors, and then use your result to write the complete factorization and list all the zeros. This time you're given 2 factors. So my zeros are negative 2 and positive 1. I'm going to use the first one, put negative 2 on the outside, list all my coefficients. I'm not missing anything and it's in order. So 2, 1, negative 5, 2. Bring down the 2, multiply it, put it in the next column, add it, multiply it, put it in the next column, add it, multiply it, put it in the next column, add it. There's the 0 we expected to get. Now, instead of using the second 0, which is 1, from the beginning, we're going to use it from our already reduced degree. So this would have been x and x squared. I just keep those values, 2, negative 3, 1, and this time I'm going to put 1 on the outside. Bring down the 2, multiply it, put it in the next column, add it, multiply it, put it in the next column, and there's the last 0 we expected to get. Now our remaining factor is 2x minus 1. So I would add that on to what we already have, and this is called your complete factorization or linear factors. And then to get all the zeros, it's negative 2, positive 1, and 1/2, what we would get by setting this equal to 0. Okay, so what happens if we don't have a single a single 0? If there's no 0, we can't factor it, right? then what we do is find all the possible rational zeros by doing plus and minus all the factors of the constant, which is going to be the last term, over all the factors of the leading coefficient, which is the first term. So we also refer to this as plus and minus factors of the last over factors of the first. And this is going to give us all the possible rational zeros, which means no i's and no square roots. These are just going to, they could be fractions, they could be decimals, they could be whole numbers, they could be positives, they can be negatives, but no square roots and no complex numbers. So then from there, we'll use synthetic division to find the actual rational zeros. So if my bank was plus and minus 1, 2, 4, and 8, for example, then I would set up my synthetic division. I'd plug in 1. I'd go through the steps of multiplying and then adding to the next column and see if it gives you a 0. If it doesn't give you a 0, then you're going to try negative 1. If that doesn't give you a 0, you try 2. That doesn't work, you try negative 2. You keep going until you get one that gives you that 0. So it'll look something like this. List all the possible rational zeros of f of x equals x to the third minus 3x squared minus 4x plus 12. Then find one of the zeros using synthetic division. Then factor the remaining. And then find all the zeros. And then we're going to talk about how the graph could help you find those zeros. So first thing we're going to do is take our polynomial and identify the first and last terms. So my first coefficient is 1. My last is 12. And the factors of 1 are just 1. But 12 are 1 and 12, 2 and 6, 3 and 4. So then I'm going to do plus and minus all the factors of the last term over the factors of the first. So it would be 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, and 12 over 1. Now let's say this was 2 on the front. I would put all of those over 1, and then I would go back and put all of those over 2. It was just 1 this time, so here's my possible roots. So if I wanted to test it out, I would put 1 on the outside. These are in decreasing degree order. Nothing's missing. Bring down the 1. Multiply, put it in the next column, add it. Multiply it, put it in the next column, add it. Multiply it, put it in the next column, and it is not 0. So now I'm going to try again. This time I can try negative 1. Bring it down, multiply it, put it in the next column, add it, multiply it, put it in the next column, add it, multiply, put it in the next column, and I've now ruled out both positive and negative 1. So I go to the next one. I'm going to try positive 2. Bring down the 1, multiply it, put it in the next column, add it, multiply it, put it in the next column, add it, multiply it, put it in the next column, and I've got my remainder of 0. So positive 2 is one of the zeros. That's my remainder. Here gets the x and the x squared, and I get x squared minus x minus 6. And the factors of negative 6, that sum to negative 1, negative 3, positive 2. 3 and negative 2 are the remaining zeros. If it had asked for it in linear factors, it would be x minus 2, x minus 3, and x plus 2. So here are the list of zeros, and here are your linear factors. Now, how could the graph have helped us if they're all real numbers? We're actually going to see them as x-intercepts on our graph. Okay, Descartes' rule is going to help you know which terms of your possible bank to try. So we're going to start to try to use that to eliminate some of those possible roots. And what this basically says is when I look at a polynomial, it doesn't matter how many terms there is, the number of positive real zeros is the same as the number of sign changes or less than the number of sign changes by a positive even integer. So what this means is if I have a polynomial, let's say it's f of x equals x to the third plus 2x squared minus 4x plus 1. Then to find the number of positive real zeros, I'm going to count how many sign changes I have. It goes from positive to positive, changes to negative, so that's one sign change. And then it changes back to positive, so it's another sign change. So it is the same as the number of changes, which means 2, or less than the number of sign changes by a positive even integer, which basically means take 2 away from this and see if it's still a number that is positive or 0. So if I subtract 2 from 2, I get 0, which means there are either 2 positive real zeros or there are no positive real zeros and 2 non-real zeros, because those come in pairs. So if I had counted the sign changes, for example, and there were 3 sign changes, then there would be 3 or 1 positive real zero. Now, when we want to find the number of negative real zeros, we're going to start by changing x to negative x and simplifying, just like we do for our test for the y-axis symmetry, and then counting the number of sign changes and subtracting an even integer until we hit a negative number. So for example, if I take this same polynomial and I plug in negative x, negative x to the third is going to be negative x to the third. Negative x squared becomes positive x squared, so this is positive 2x squared. Negative 4 and negative x is positive 4x plus 1. So here's one sign change, and then it stays positive, which means there is one negative real root. And we can't subtract 2 from that because then it would be a negative number, which we don't want to use. So then we would say it's exactly one negative real root. And this is why Descartes' rule is helpful. Because if I had a full bank of all the possible roots of my function, positives and negatives, and I knew that there was either going to be 2 or no positives, but there was going to be there was guaranteed one negative, then when I go to test out my positive and negative roots from my possible bank, I'm going to start with the negatives because there has to be a negative. All right, so let's look at some scenarios. I realize these are a little bit blurry, but if we just pay attention to the signs, okay, and to the exponents, this one starts positive, goes negative, that's one sign change, stays negative, but then changes to positive, second sign change, stays positive, but then changes negative, third sign change. So there's 3 sign changes, which means there are 3 positives or there is 1 positive real root. Now, if I were to change these to negatives, the negative x to the 7th would make this negative 3x to the 7th. A negative x to the 5th would also change that sign, so it would be positive 2x to the 5th. A negative x to the 4th is going to go away. The negative's still in the front, though, so it would be negative x to the 4th. A negative in the x squared is going to go away, so positive x to the 2nd. Negative x and negative 3. There is 1 sign change, 2 sign changes, 3 sign changes, 4 sign changes, and then it stays the same. So there would be 4 or 2 or 0 negative real roots. And the next one, there's only 2 sign changes, so it's 2 or 0 positive real roots. If I plug in a negative 5, negative x, I'm going to get negative 4x to the 5th plus 2x to the 4th minus 3x squared minus x plus 5. And in this case, there's 1 sign change, 2 sign changes, 3 sign changes. So there'd be 3 or 1 negative real root. And last one, only 1 sign change, so there's 1 positive real 0. If I plug in a negative x, on the evens, it's going to go away. So negative x to the 6th minus 5x to the 4th minus x plus 9. And that is one sign change. So there's one negative real root. All right, example 9 is going to put all this stuff together. I'm going to bring in Descartes' rule so that we can practice it. And then we're going to use a graphing utility to help us out. So f of x equals x to the 3rd minus x squared minus 4x plus 4. How many positive and negative zeros are there? Here's our Descartes rule. So if I look at this, it starts positive, it changes to negative. That's one sign change. Stays negative, changes to positive. That's two sign changes. So there are 2 or 0 positive real roots. Now let's change these to negatives. Negative x to the 3rd minus negative x squared minus 4 times negative x plus 4. I get negative x to the 3rd minus x squared plus 4x plus 4. And this time there's only one sign change. So 1 negative real root. Now let's talk about your possible roots. So it didn't ask for these, but if I wanted to try them out, it would be plus and minus the factors of last over first. Last being 4 has the factors of 1, 2, and 4. First being 1 means this is plus and minus 1, 2, and 4. Now, if I went without using my graphing utility to help me out at all, because I know there's has to be one negative root, I would test the negatives first. So I would test -1, then -2, then -4 before I move to the positives. But we're going to use the graphing utility to find one of the real zeros. So let's do that. Okay, so now that we can see, I went and graphed it, and there are 3 real roots, okay, which means we're going to find more, but the one negative real root was -2. So we were right that there was one negative real root. So now, if we didn't use the graphing utility to find the remaining ones, and we practice our synthetic division, -2 would go on the outside, 1, -1, -4, and 4. Bring down the 1, multiply it, put it in the next column and add it, multiply it, put it in the next column and add it, multiply it, put it in the next column, and I get 0. There's my remainder. -3 gets the x, 1 gets the x squared. And from x squared minus 3x plus 2, we can factor x minus 2 and x minus 1 to find our remaining 2 zeros, which are also reflected on our graph. So what are all the zeros? -2, +1, and +2. Now that wraps up where we're going to stop for today. The good news is we leave just a little bit for tomorrow's video and some practice with the warm-up. I would say that this is similar to your test question, except this is factorable from the beginning. Yours won't be. And also you can get all your zeros from your graph. By the time we get around to test, you'll see that we're going to change this a little bit. You'll only get one real zero, and then you'll have to use like the quadratic to find the remaining ones. But we'll practice that more towards the beginning of next week. All right, please don't forget to submit your notes so you can get the easy 100 for today. You can begin to work on 2 3s homework if you want. It's not due until the day after tomorrow, but it would be good to get a head start so it's not all left for tomorrow. I hope you guys have a great day.